Okay, so we've already seen how useful CFTs are. They're useful to understand the space of quantum field theories. They define the starting and ending point of RG flows. And we've seen that they're also very useful for the description of phase transitions. But we haven't actually given any examples of conformal field theories. So that's what I want to start doing now. And I want to explain some of the methods that we've got to construct them. So we do know a few simple examples of conformal field theories. So for example, a free massless scalar field, that's a good example of a conformal field theory. We could also have taken a free fermion. That could be a Majorana fermion. It could be a Weil fermion, or it could be a Dirac fermion. All of those free fermion theories define conformal field theories. Or we could also have looked at the free gauge field and the gauge invariant observables of a free gauge field also defined a conformal field theory. However, none of those examples are very interesting because they're all free theories. So I want to start showing you how do we construct conformal field theories that are interacting. These are more non-trivial examples. The first example that we're going to consider is what's called the Wilson-Fisher fixed point. So this is called the Wilson-Fisher CFT or the Wilson-Fisher fixed point. Good. And the reason, so this CFT obviously was discovered by Wilson and Fisher. When it was discovered, it was really quite a breakthrough. And we know how to construct many other conformal field theories using this logic. And it's called a fixed point because we'll actually flow to this conformal field theory at very low energies. So here you're seeing an example of a CFT that lives at the endpoint of a renormalization group flow. So how do we get this CFT? Well, let me give you the Lagrangian. So the Lagrangian of the CFT, so we start off, it is a massless scalar field. So we've got the usual kinetic energy, 1/2 d mu phi. And then there is a self-interaction, which is plus g over 4 factorial phi to the 4. Now, let me just remind you, this is quite common notation. Certainly, I used it in my first quantum field theory course. Notice that it looks as if the potential has got the wrong sign because there's a plus appearing here. Well, when there's that plus appearing there, I'm giving you a little nudge, and you should know, okay, I am working in Euclidean space. Okay? And for this example, I'm going to work in Euclidean space. We can define the Wilson-Fisher fixed point in Minkowski space, no problem with doing that, but often we work in Euclidean space. And for this example, I'm going to work in Euclidean space. To work out what is the Wilson-Fisher fixed point, we're going to need to work out the beta function of this theory. Now, we did this in our Introduction to QFT course, so I'm just going to give you a very quick reminder on how to calculate the beta function. And remember the basic observation that we started from, we looked at the Green's function. So I'm going to denote the Green's functions of n fields. I'm going to denote this by Gn, okay? And actually Gn will be a function of n coordinates. What is it equal to? It's the vacuum expectation value. That vacuum doesn't look great. So it is the vacuum expectation value of the time-ordered product of n fields. That's what it's equal to. And you can Fourier transform this to momentum space if you wanted. This is the position space Green's function. Just a few things. We know that all of the Green's functions with n odd vanish, but we know that the Green's functions with n even are non-zero. And there's an infinite number of those Green's functions with n even. Well, this infinite family of Green's functions obey, so these all obey the Kalan-Szymanczyk equation. Very important equation in quantum field theory, one of the really important equations in quantum field theory. What the Kalan-Szymanczyk equation tells us is that if we take m d by dm plus beta d by dg, the coupling, plus n gamma on the Green's function Gn. So here I'm thinking in position space. Obviously, we could have done this also in momentum space. That's zero. So let's just explain this a little bit. So here the beta that you see in this equation, this really is the beta function of the theory. And the gamma that you see in this equation, this is the anomalous dimension. So in a CFT, beta will vanish, but gamma, the anomalous dimension, will be one of the very important observables that we have in a conformal field theory. M is the scale at which we perform the renormalization. So, when you start to calculate correlation functions in this quantum field theory, you'll find some of them are divergent and they need to be defined in some way. The counter terms help us to define the theory. And those counter terms have to be set. They would be set by some experimentally input numbers through a set of conditions called renormalization conditions. And the scale at which you apply those renormalization conditions is the scale m. So the Kalan-Szymanczyk equation is telling us how to relate two CFTs that have been defined at slightly different scales m, so that they will give you all the same physical predictions. Now, how would you use this Kalan-Szymanczyk equation? Well, you could compute any two Green's functions, but it will be simplest to compute G2 and G4. Once you've got them, plug them into the Kalan-Szymanczyk equation. You'll get two independent equations, one for G2 and one for G4. From those two independent equations, you can read off beta and gamma. So that's how you'd use the Kalan-Szymanczyk equation. Okay, so let's just talk about what your normalization conditions could be. So let me just say normalization conditions. So I'm being very quick in this discussion. I hope this is just refreshing things that you already know. If not, go back and look at your first course on quantum field theory. You could also go back and look at my lectures on YouTube. So what would we do? Well, so actually we would usually apply the normalization conditions in momentum space. So if you've calculated a position space Green's function, you would need to do a Fourier transform, but that's no big deal. And then the first renormalization condition would be on the 2-point function at momentum p, and it would say, set the 2-point function at momentum p to be equal to I over p squared. So this is an equation that the 2-point function must obey, and we would do this at p squared is equal to minus m squared. Okay, so that's your first equation that your 2-point function is satisfying. There's only one momentum that appears because if you have a 2-point function, so this blob would be a whole sum of all sorts of Feynman diagrams you can draw. But if you have a momentum p flowing into that blob, you must have a momentum p flowing out of the blob. Let's also look at the 4-point function. What's the renormalization condition? So, by the way, we would have a finite number of renormalization conditions in this theory, and they would be set by the 2- and 4-point functions. So we would say the 4-point function, and now I write down all four momenta. And the reason why I write down all four momenta is that if you look at the 4-point function, we can have a momentum P1 on this leg, we can have a momentum P2 at this leg, P3 on this leg, and P4 on this leg. And we know, for example, the conservation of momentum would tell us that these four momenta sum to zero. Now, it is not G4 itself that we put the condition on, it's G4 prime. And what that prime means, so I'll come back to what that prime means in a moment. Let's just write down the conditions. So we usually say that this is equal to minus IG. Oh, sorry. We would usually set this equal to minus IG. And we again have to set this at some point. And the point that we choose is P1 plus P2 squared is equal to minus m squared. So this is some kinematic point. And I also fix P3 plus P4 squared equal to minus m squared. And then I also set P1 plus P4 squared equal to minus m squared. Okay. And of course, the momenta are conserved. So that's the renormalization condition. Now let's just come back to what does prime mean. So prime means that you remove the external legs. So you'd pull the legs off, you'd only be left with this blob sitting in the middle. And so remove the external legs. Often people say amputate the external legs. A little bit more graphic. And the other thing is we only want the connected piece. Connected piece. Okay. So let's just say what Feynman diagrams you would sum. So for example, if you are looking at the 2-point function, now I'm going to write down the Feynman diagrams in momentum space. So really go back to the YouTube videos if you need to, or back to your first course. So if we were working to one loop, well, there's the tree diagram. Then at one loop, we would also have that diagram contributing. So with some of those two diagrams, that would give us G2. Now, if we looked at G4, so let's just do this slowly. So for G4, what would we have? So for G4, we could have the two particles propagating along like that. Actually, we could have the two particles propagating along like that. We could have the two particles propagating along like that. And we could have the two particles propagating like that. Then we could have a diagram that looks like that. At one loop, we would have things like this. We could have this. And we could have, let's draw it like that. And like that. So those would be the four, the three one-loop diagrams we could have. But then we could also have stuff where we dress one of these legs. Okay. That would also be a one-loop diagram. And this would be a one-loop diagram. And of course, I could have dressed the lower leg. And I could have dressed that leg. So it quickly becomes a mess, as usual in quantum field theory. And if we were going, sorry, we should also include this one. That one also gets included. And, you could have dressed any of those four external legs, so off it goes. Now, what does G4 prime look like? Well, G4 prime will be a small subset of these diagrams. And that's the diagram sitting over here. So this is what G4 prime would be. Okay, much simpler. So let's just discuss this a little bit. Okay, good. So on the very first line, we don't include any of those diagrams in G4. So now I'm looking at this expression for G4. So I'm looking at this expression over here for G4. So on the very first line, we don't include any of those diagrams because they're not connected. Those are disconnected, okay? And what did the amputate mean? It means remove the external legs and keep only the connected piece. Then the second line sitting here we would have, let me maybe just stress something, don't include these external legs. I'll just draw a little red dash through them to indicate that these legs are actually dropped, okay? All of these external legs are dropped. Then the third line in this blue box, we also wouldn't include because those are also disconnected. The fourth line is also disconnected. Now, the fifth line we don't include. The first diagram on the fifth line, this one, once you've dropped the legs, is just the diagram that I've shown. So those ringed green diagrams are both represented by the single diagram down the bottom here in this G4 prime. So that would be the G4 prime. That is what would appear inside your renormalization condition. Now, there's many different ways of picking renormalization conditions. You can decide to pick different kinematic points. You could choose to vary your scale. All of these different choices that you make are part of what's called your renormalization scheme. And if you calculate anything physical, it should be scheme independent. But in particular, one of the choices of your scheme is the scale M, and it's the scale M that the Cullen-Szymanczyk refers to. So the d by dm in the Cullen-Szymanczyk equation is talking about making a small change to your renormalization scale. Good. So that's the actual quantities that we would actually calculate and then plug into the Cullen-Szymanczyk equation.